Okay, so there was a timer on the camera, so it stopped at the 60-minute mark where we were finishing up with that natural spline, right? Which was the last thing that you guys saw. So let's continue, right? So this is my natural spline based off of these constraints, right? So let's talk about clamp spline, right? So I want to do the clamp spline now, right? So these constraints are not correct, right? These are the constraints for the natural spline, right? Then my second derivative has to be equal to 0 at that particular location, right? So let's talk about the clamp spline. And in the clamp spline, we want to make sure that the first derivative is equal to 0 at that location. So let's erase these two guys right here. Okay. So for my clamp spline, for s of 0 prime at 1, I want it to be equal to 0. So let's put that in. So we get 3a sub 0 plus 2b sub 0 plus c sub 0 is equal to 0. And then s of 1 prime at 3 is supposed to be equal to 0. So we have, what is that going to be, 27, I think 27, a sub 1 plus 6, thank you, 6 b sub 1 plus c sub 1 is equal to 0, right? I want you guys to notice that none of my other equations are changed, right? So I still have the first 6 equations that I had before. So it's very easy once you have the natural spline typed into your calculator, right, in matrix form, right? To get the clamp spline, the only thing you have to do is change the last 2 rows, right? The last 2 rows of your matrix to mirror what has happened. You go from the natural spline to the clamp spline. So we have different conditions for our last 2 equations right here. So what do we get when we type this into our calculator, find out what A0, B0, C0, D0, A1, B1, C1, D1 are, right? What do we get? Let's write that here. I don't want to erase this one, so I'm going to put the answer to the clamp spline right here, right beside the answer to the natural spline. So we have a solution. Here we're dealing with the clamp spline. Clamp spline solution. Okay. Now if we do this one, what I have is A0 is equal to 1/4. B0 is equal to 0. C0 is equal to -3/4. D0 is equal to 5/2. Okay. So a little bit nastier numbers than we did for the quadratic, right? And we got for the quadratic. And then we have A1 is equal to -7/4. B1 is equal to 12. That's a nice number. C1 is equal to -99/4, and D1 is equal to, I have 37/2. Okay. And this is what I have. And so what is going to be my final answer for my clamp spline, right? So we get S of X is equal to, put that here, 1/4 x cubed minus 3/4 x plus 5/2, right? X goes from 1 to 2. And the other one, I have -7/4 x cubed plus 12x squared minus 99/4x plus 37/2. And I don't have enough space, so x goes from 2 to 3. I just put down here. And I'm going to box this guy, right? We're going to color code it, right? Here I had blue for the natural spline, right? And I'm going to use green for the clamp spline. And here's my answer, right? I want you guys to notice that these two splines do have, they do have some numbers that are in common, right? We have a 1/4 here, -3/4, -3/4 there. But in general, the numbers are completely different, right? And the functions are completely different in terms of the cubic polynomials that we're getting, right? So don't think that necessarily that you're going to get, when you do go from natural spline to clamp spline, that all of your values or most of your values will be the same. They're going to be changed based off of these two conditions that we have. placed on our spline. Okay, either the natural constraints or the clamp constraints. Okay, so that's pretty neat. So let's talk about one more thing. We're almost done. I want to talk about, in general, when do we know that something is a spline? So suppose somebody gave me a function. I want to know, is it a spline or not, right? Is this thing a spline? So that's what I want to talk about now, right? How do I know when something is a spline? This is our last topic in splines, and we'll be done with that. And you guys will have homework and things that will be based off of that and everything, right? So here we have definition. A piecewise function S of x is a nth degree spline. Okay. If A, each individual function S of ix, right? S of ix is a nth degree or less polynomial. B, the functions S of x, S prime of x, all the way up to the n minus 1 derivative of s at x are continuous. On the interval from t naught to t sub n, right? So this is my endpoints of my function. In our case, our t naught in our last example was 1, right? That's our first point. And our t sub n, our last point, was 3. Okay. So essentially, if this is a cubic polynomial, it has to have each individual function has to be a polynomial of degree 3 or less, which this one is, right? And then we have to have that all of my derivatives. My function s has to be continuous, so these guys have to meet. The derivative has to be continuous, so that these guys meet. The first derivative meets at 2, right? And then my second derivative is continuous, right? So the second derivative also meets at 2, right? So it's a continuous function overall. So this is what we wanted to talk about. So let's look at an example. We're almost done. It's good to look at this just to make sure that we understand. We know how to construct a spline. But how can we, if we are given a spline, or if we're given a function, how do we know it's a spline, right? Or what type of spline is it? Okay. So here I have show that the function below is a quadratic spline. And here's my function. I have s of x is equal to 3x plus 1. X goes from -4 to 0. X squared plus 3x plus 1. Okay? X goes from 0 to 4. I want to show that the function below is a quadratic spline. Okay. This is my goal. This is what I want to do. Now let's look at this, right? Let's look at this. Let's take it step by step. Are each of these functions, or each of these individual functions, a second degree polynomial or less? The answer to that question is, yeah, it is, right? This is a first degree polynomial, which is less than a second degree. This is a second degree polynomial. So each of these individual functions are second degree polynomials, somewhere right here. Erase this now. I could say here with this problem A, s of 0, x, which is equal to 3x plus 1, and s of 1x, which is equal to x squared, plus 3x plus 1, are both second degree or less polynomials. So I'm going to give myself a grade. Suppose that this is on a test or a quiz like that. I'm going to say, yes, this is correct. Check. That's right. So the first part of this definition is correct, right? It's the second degree. Now, are the functions, right? We want to be able to say, are the functions s of x and s prime of x continuous? Right? Because remember, in this case, my n is going to be equal to 2. My n is going to be equal to 2 because we're dealing with a quadratic. We're dealing with a quadratic spline. My n is equal to 2, right? So 2 minus 1, I'm looking at the first derivative, all the way up to the first derivative. So from s of x and s prime of x, I want to make sure that both of those guys are continuous. Are they continuous? Now, we got to make sure that we remember our algebra, right? Polynomials are continuous everywhere. Okay. So we know that 3x plus 1 is a continuous function. We know that x squared plus 3x plus 1 is a continuous function. The problem is we need to make sure that for this function s of x to be continuous, the 3x plus 1 and x squared plus 3x plus 1 both have to connect. They have to meet at a location, right? So we need to show that s of x and s prime x is continuous, are continuous. Can I spell continuous? I don't know. Add, where do they meet? Where do these two functions meet? Where are the places where they're going to be able, where are these two functions, 3x plus 1 and x squared plus 3x plus 1, where are they going to meet for this piecewise function? They're going to meet at the value of 0. That's where they change rules, right? We want to make sure that they're continuous at x equal to 0. That's what we want to do. At x equal to 0. So let's look at s of x real quick. So s of x, we want to show that s of 0 at 0 is equal to s of 1 at 0. Are these two guys equal? Okay. So if I plug in 0 into this function and into this function, are these guys equal at that location? And when we plug it in, we get 0 plus 1 equal to 0 plus 0 plus 1. 1 equals 1. That is true. So we give a little check there. You're correct. Right. These guys are equal. Are we done yet, though? Can we stop here and say that this is a quadratic spline? No, we can't, right? Because we need to show that the derivative is equal at 0 as well. So let's find the derivative of s of 0x and s of 1x. So s of 0x, its derivative is going to be 3. Okay. S of 1x, its derivative is going to be, what is that, 2x plus 3? Put that in a little cloud. Those are the derivatives. Now let's check to see if the derivatives are equal at the place at 0. So we're going to do s of 0 prime at 0. Is it equal to s of 1 prime at 0? Is that true? Well, if we plug 0 into s of 0 prime, we get 3. Plug 0 into s of 1 prime, we get 0 plus 3. So 3 equals 3. This is a true statement. So again, we give another check. Yes, right? And now we can say, now that we know we satisfied both of these conditions, right? We satisfied the first condition that each individual function is an nth degree or less polynomial, so second degree or less polynomial, which it is. And we've shown that each one of those functions is continuous, right? They meet up, the original function and its derivative meet at that location of 0, right? Which is the only place where we might have issues with our spline, okay? So I can say yes. S of x is a quadratic spline. Is a quadratic spline. Okay. Here's our last problem, and we're done. Last problem. Last problem. Let me get the right paper. Here it is. Show that S of x is not a cubic spline. Now, I don't care if it's a natural spline or a clamp spline or any other type of spline, as long as it is a cubic spline, right? Show that S of x is not a cubic spline, and here's my S of x in this case. S of x is equal to x plus 1. X goes from -2 to 1. -1, sorry. -2 to -1. I have x cubed minus 2x plus 1. This function goes from -1 to 1. And I actually have one more part of this, right? So I have x minus 1. And this one goes from 1 to 2. Show that S of x is not a cubic spline. This is what I want to do here. Show that S of x is not a cubic spline. So I have S of x is equal to x plus 1. X goes from -2 to -1. X cubed minus 2x plus 1. X goes from -1 to 1. And then the last one is x minus 1. X goes from 1 to 2, right? So I want to show that this is not a cubic spline. So essentially what I need to do is I need to see which one of these two rules breaks, right? Which one of these two rules that we have to have for a nth degree spline, which one of these two rules breaks, okay? So what we need to figure out. Okay, well, some of you guys have probably already started on it. Hopefully you paused the video, right? Maybe like Dr. Webster didn't say pause the video, but here I am. I'm gonna say pause the video right now. See if you figure out if this is, why this breaks. Why this is not a cubic spline using these two rules. What is wrong with this? Pause the video, figure it out. I'll wait for you. Well, welcome back. Did you figure out why it's not a cubic spline? Well, let's look through it. Let's look at the first condition. A, Here we have s of 0x, right, which is equal to x plus 1, right? We have s of 1x, which is equal to x cubed minus 2x plus 1. And we have s of 2x, which is equal to x minus 1. And these are all third degree or less polynomials. So there's no issue at all. There's no issue at all with number A, with letter A. This is a check. No issues at all. There's no problem with that. All of these guys, each one of these functions are, each one of these functions is a third degree or less polynomial. This is first, this is a first, this is a third. Okay? No issues there. The issue must be in B, right? There must be something wrong with B, right? So either s of x, s prime of x, or s double prime of x. One of these guys is not continuous, or more than one of these guys is not continuous. To kind of help us with that though, let's put down s prime of x. What is s of 0 prime of x going to be equal to? That's going to be equal to 1, right? S of 1 prime of x is going to be equal to 3x squared minus 2, right? S of 2 prime of x is equal to 1. Right? S double prime, let's put that one as well. 0. For s of 1 double prime is going to be 6x, right? And then s of 2 double prime of x is going to be 0. Okay, so we have all these guys down. So let's check. Let's make sure where do these functions meet, right? We remember that the polynomials are continuous everywhere. We're only going to have issues where they meet, where the functions meet, right? So the places where these functions meet is when x plus 1 and x cubed minus 2x plus 1 are going to meet at -1, right? X cubed minus 2x plus 1 and x minus 1 are going to meet at 1. So we need to look at both of those locations, right? So I'm going to say, okay. All right, we need to check interior nodes, interior knots, I should say. I need to see is s of 0 at 1, -1, equal to s of 1 at -1. I need to check is s of 0 at 1, or s of 1, sorry, at 1 equal to s of 2 at 1. I need to check both of those, see if that is the situation. All right? So s of 0 at -1 does it equal to s of 1 at -1. So let's plug in -1 into s of 0. If we plug -1 into s of 0, we get 0. So we get -1 plus 1. We plug -1 into s of 1, we get -1 plus a 2 plus a 1. This gives me 0. This also gives me 0. That checks out this true statement. True statement. All right. So no issue with that one. What happens when we plug 1 in to these two functions right here? If you plug 1 into s of 1, you get 1 minus 2 plus 1 equals, plug 1 into s of 2, you get 1 minus 1. We know that this is going to be 0, and this is also 0, so this one checks out. So no issues. That means that these guys do meet, so it's going to be continuous, right? Our function is going to be continuous. S of x is continuous on the interval. So like I said, S of x is continuous. Okay, S of x is continuous. No issues there. But what about S prime of x? S prime of x, is that guy continuous? Well, we need to check the same thing again, right? So we need to look at what is S of 0 prime at -1, is that equal to S of 1 prime at -1? So let's plug that in. Just like we did here, now we're doing it for the derivative. Plug into our derivative here. So -1 into s of 0 prime is going to be 1. -1 into s of 1 prime gives me 3 minus 2. So I get 1 is equal to 1. That checks out. Good to go. Let's try the other one, right? At 1. So s of 0 prime at 1, does that